This is something that it's an issue that's very dear to me. It simultaneously fills me with rage, and also my father is colorblind, so it is very difficult for him to see what I do if I do things poorly. I understand that people, maybe some people, a lot of people, scientists, think that color is not important in visualization. I'm here to tell you that's not the case. I know some here, people agree with me on that, but anyway, let's start. So this is not my work, and this is not just going to be a bitching session. We are going to do actual science, and I'm going to show you why the wrong color map is really bad. I'm going to do it for a specific one that's particularly bad that you are all very familiar with. And then the next talk is Kristen's talk, and Kristen will delve into some more of the specifics for the color map, specifically with Matplotlib. For this specific talk, I have pulled literally all of the information from this link, and these slides are on GitHub, and the link to the slides is at the end of the talk. So this is not my work, this is somebody else's work. Okay, so an introduction. Data is a huge aspect of science. No one here disagrees with this. We have a buzzword for data being a huge aspect. It's called big data. So no one here disagrees with me. By and large, we scientists treat data reasonably well, and some of us visualize it extremely poorly. Why? It's not intentional at all. It's sometimes by complete mistake or misunderstanding. And the reason we visualize it poorly is through color maps. And there is a mathematical reason why color maps are incredibly misleading. So your data, usually, so I'm talking 2D here. So your data is 2D, it lives in some domain in the plane, and it maps to something in the reals. And we're just going to normalize so it's between 0 and 1. Okay? So everything's bounded, everything's fine. A color is assigned to each one of those values. Okay? A color map is another function. It takes those numbers that you're assigning, and it assigns a color to them, and a color lives in a three-dimensional space. It's either RGB or HSV or whatever parameterization you choose, but it's a three-dimensional object. So I'm now visualizing something that's ostensibly 1D with a three-dimensional object. And for those of you who were here last year and saw Matt Terry's talk on the Professor Manta Shrimp, he designed a color map that was an honest-to-God, and I kid you not, an honest-to-God knot in 3 dimensions. A knot. So this thing loops around itself inside and joins with itself in 3-dimensional space. And you're mapping that to a 1D object. How many people here think that makes complete sense? Thank you very much. The point, color maps can be extremely misleading. Okay, so let's do a little thought experiment. Who knows what this is?
And it's a hard video.
Shut up, Kyle. You saw me write the talk. You at the back.
Florida.
Oh my God. Okay. This is Florida. Here's 2 of them side by side. One, so the left-hand side is jet. Oh yeah, I'm going to dump on jet for the rest of this talk. That's the color map. The right-hand side is something that's not a continuous color map, but it's using some domain expertise to pull out the shoreline. So the person that made this knew what their data was and knew what they were looking at. Who thinks the color map on the left is better than the color map on the right? Thank you. Okay, left, linear interpolation RGB space between red and blue. That is jet. That's what happens. The right, changes in data is perceived as proportional changes in color. That's what you strive to see. You want to see the equal jumps in data give you equal jumps in color space. Perception is very subjective, so this is not, I mean, there is some science behind it, but it's an incredibly subjective issue. And as I've said, there's domain-specific knowledge going on. And now I'm just going to go through a couple more examples of how bad jet is. So I should add, there are color maps worse than jet. So this is not the bottom of the barrel, okay? So the left is a Gouraud shading, 3D render Gouraud shading. The light source is at the viewer, and it's supposed to explain what the data really looks like. This is also subjective, but it's doing a reasonably good job. So this is Chesapeake Bay, and the blue here is the Potomac, I don't know how to pronounce that, but this is a river here, and it goes up to Washington. And so look here, the sea level here is fairly constant, and it's fairly constant up here, and then the land sort of continuously comes in. In jet, the tributaries stop here, and the rest are masked by this cyan color. So this is clearly, I mean, something is going wrong here. There's some masking. This is actually a much better example. Also, these pictures are really pixelated. I'm sorry, I copied and pasted them from the article. So this is a T2, which is a measure you take from an MRI when you scan a human brain. Notice, so there's lots of nooks and crannies here, and on the right-hand side, it's uniformly cyan. And in fact, if you look at the scale, cyan covers 150 to 300. So it's a 2 multiplied by 2 change in the data is mapped to almost the same color. So this is completely misleading. Here's another example. This is turbulent noise from a jet engine. And on the left, you can see there's lots of turbulent high-frequency stuff going on here, and lots of undulation, low-frequency undulation in this direction on the left-hand side here. None of the high-frequency data is observed here. Look at this. It's completely gone. And on the right-hand side, this basically is uniformly green. So we've lost all frequency information because of this banding, this segmentation that happens between cyan and green, and sometimes red too. This is another, so this example is a lot smoother. So this is low-frequency data of the Earth's magnetic field. The axis, this top axis here, the top line is all the North Pole, so they're all the same point. And the bottom line is the South Pole, they're all the same point, and the equator's in the middle. So on the right-hand side, look at this green band here that separates the equatorial magnetic field and the polar magnetic field. It looks essentially discontinuous. So you vary, and then you hit the screen, and then you're yellow. This is a really terrible color map for understanding the structure of your data. All the structural information is gone. Last example, which is not physically inspired, is the sinc function, which is sine x over x multiplied by sine y over y. And it's at the origin, it's 1. And look, so there's a nice steep gradient here coming up this peak, and then around the outside are these troughs with a shallower gradient. And look at the peak. So you get this banding. So you have the cyan band, the green band, the yellow band. So this essentially looks like a step function. Looks like it's doing this, right? That's clearly not what's happening in the data. How do we fix it? What have we learned? JET is not a great color map. Or is it? So it's a terrible color map for understanding the form of your data, the structure. How am I doing on time? 3 minutes? Okay. It's a terrible color map for understanding form or structure. It's an okay color map for looking at a specific point of your data and understanding the value. But even that's not great, because when we get that banding. So as I've mentioned, there's 2 types of information, metric information and structure information. JET is awful for form and sometimes okay for value, but not everywhere. JET is not alone, but it is very commonly used. Remember I said JET is not the worst color map. You're about to see some pretty bad ones in the next talk. So how do we pick a good color map? Well, the answer is it depends. As you've seen, there's high frequency data, there's low frequency data, and here's a very good example. Oh, actually, let me do something else first. But you should read this paper here by Colin Ware, which talks about how to understand high frequency and low frequency data. And all these slides are online. I'll show you the link at the end. So color has 3 dimensions. Hue, saturation, luminance is one particular parameterization. There's also RGB and a bunch of others. From the paper, saturation varying color maps are very good at understanding changes in low frequency data. Saturation is basically when colors fade in and out. Okay? Luminance varying color maps are good for high frequency data. Luminance is basically how bright a color is, so how black or how white it is. The human brain is incredibly bad at interpolating hue. Hue is the thing that assigns names to the values, so green, red, those are all hues. Okay? Q, perceptually-based color maps. Perceptually-based color map is defined to be a color map that gives you equal jumps in color given equal jumps in data. So your brain perceives this. A Okay, so here's a good example. So on the top left is jet. This is a map of southern atmosphere. It's measuring ozone in the southern atmosphere in spring. It doesn't matter. So here, this is uniformly blue. You get the cyan band, etc. The top right is a luminance varying color map. It goes from black to white. There's no saturation. There's no hue. It's black and white. And you can see all this high frequency information here. The bottom left is a saturation varying color map. It goes, so we have an achromatic color in the middle, and then saturate green from the bottom and saturate red from the top. You don't see so much of the high frequency information, but you see the low frequency information. You see these changes from red to yellow. And at the bottom right is a mixture of both. And actually in the paper they didn't tell me how they did it. They just say, we take the best of both worlds. And you can kind of see there's high frequency information you can still garner here that you can't hear, and maybe here too. And the low frequency information is still there as well. So this is arguably much better than both of these, and definitely much better than this. If you picked either the top right or the bottom left, I'd be happy with your publication. If you'd pick the top left, my father would not be able to read your plot. I think that's a fair thing to say. I have some more examples, but actually I'm just going to skip to the end. I've just done perceptually-based for each of them, and I'd like to thank you, and I'll take questions.
Thank you, Damon. Actually, we're going to